today's lecture in the OLS estimation and its expected prediction squared error. So what is the error in the future? From OLS regression estimation, the simplest setting y depends linearly on one input variable x. But more importantly, we'll see if in this setting we can beat OLS with another model. So this is the most favorable setting for OLS. So we have linear relation with some error, and the error is white noise, normally distributed with a mean 0 and variance 100 or standard deviation 10. So what do we have? Y equals ax plus b, a is 1.5, b is set to 2. We have a training data set. Here is x and y. These are the blue points. How the y's are generated. They are generated from the mean of y, which is ax plus b, plus error. So we have generated like points around the line ax plus b. And here's the error. The ax plus b line is drawn as well. It's the orange line. So this is the model that generates the data with some noise. And this is with gray, our OLS estimate from our training data sets. So it has different coefficients. So a is not 1.5, but it's computed now as 0.97. I'm using the line-est function to estimate the coefficients a hat and b hat. So what is the error in the future from this OLS prediction line? So if we fix the line, at each point, let's say x equals 6, we'll have lots of points. So each time we have a training, a test set. So we have another point that is generated around the orange line. And our prediction is fixed. It will be fixed by our OLS regression line. So when it's fixed, what is the expected error? Squared error. So the difference between what we see in the future and our prediction, and it's here. So for x equals 6, it will be 112.97. How do we calculate it? It's just equal to the difference between the truth and our prediction. So the truth is 11 should be ax plus b, but we predict 7.40. So this thing squared plus the variance of y is giving us what is in the future the expected error at this point. So at different points, it's different just because the difference between our prediction and the truth is different. So how do we calculate it? This expected error, variance of y plus the difference between prediction and truth. It comes from here. So at each point x, our expected prediction square error for the future, so for x equals 6, for example, is y minus mu hat, our estimate squared, and this can be decomposed into, we just add and subtract mu from it, and then this is equal to the variance of y plus this term plus mu minus mu hat. So because OLS is unbiased estimator in this case, expected value of mu hat will be equal to mu. Therefore, this term will be 0. And what we'll have is just variance of y plus difference between prediction and the truth squared. So this is our prediction in the future. But we can compute it only because we knew mu. We know what is the truth. So here it is. Can we have another model? Another model here. So it's exactly the same model here to the right. So it's exactly the same model as the OLS model. Here's OLS, but we just multiply our y hat by alpha, and alpha is 0.95. So whatever is our prediction, we just multiply this prediction by 0.95. Very interesting idea. What do we get? Okay, let's multiply it by something even smaller, so that we have here the green line. So the gray line is from OLS, and the blue one is whatever was our OLS prediction times 0.8. So we can see 0.1, then the blue one is almost 0, because y hat is whatever it was multiplied by something very close to 0. I mean, if we multiply by 0, we just get the green line that is flat, so y does not depend on x. And if it is 1, we have exactly the same solution as OLS, but let's multiply by, let's say, 0.25. So the green line is just a little bit below the gray one. It's a little bit flatter, and it's rotated around 0, by the way. So for y values below 0, the green one is above the gray one. You can see that here. Okay, let's see here, and then for y values above 0, the green line is below the gray one, and this is called penalization towards 0. So whatever was y hat from OLS, we just multiply it by a constant that is between 0 and 1. So this is called penalization towards 0. So can we conclude that this is a better model? So we have OLS in the greatest possible setting for it. We have linear regression, we have normal errors, but then whatever we get from the linear regression, we just multiply by 0.2095, and we see what is the error per point. Again, it's calculated in the same way as before. We have prediction, and around this prediction we have future test points that go around it. We always compute the squared error, infinitely many squared errors in the future, and then we get that this is the expected squared error in the future for each x. And overall it was 101 for this specific training dataset. So for the OLS it's 102, on average it's 101 for the let's say alphaOLS model. Of course, alpha is between 0 and 1, 0.95 in this case. But for another data set, it could be different. So it could be, okay, it could be like here, that for the OLS, we have the error is 102, expected error overall x, but it's 103 for this training data set for the alphaOLS. That's why, in order to conclude a proper experiment, we just have extremely many data sets, I think around 100. So we have at the same x, we could observe either this y or different y. Then we have different regression line. We could have started with these points, etc., or these points, or these points, and so on. In each time, for each training data set, we know what will be our error. So if we have started with that training set, this will be. If we started with that training set, this will be. Start with that training set, and so on. So we generate 10,000, let's say, I don't know how many, extremely many training data sets here. And let's see what is the average prediction squared error over these training sets. And it's 117. So if we started with this training data set, it was that. With this training data set, it was that, and so on. But for the same training data set, we also have the expected error from the alphaOLS model. And on average, here it's 116. So it's less than the OLS one. So when alpha is 1, they're the same. When alpha is a little bit less than 1, So this one starts to be less than that. If alpha is 0.95, less 0.9, it's again less. Okay, we repeat the experiment. It's less all the time by around 2-3%. And this is a big penalization, by the way. 0.9. It means that whatever we see, we make it 10% less towards 0. It's a very big penalization. Can we go further? So if you go 0.8, so it is still less the error than the OLS one. So we just say whatever we see, we just say 80% between. So we just multiply it by 0.8, which is we make it less with 20% towards 0, which is a very, very big change. What about 0.7? So we make the line flatter and flatter. 0.7, so we have more or less the same results, or OLS is starting to get a little bit better. So at 0.2, it's very, so it's a flat line. We have very big now error. So what was optimal? Maybe around 0.9. So always there exists an alpha below 1 that will make sure that our expected error is less than the OLS. And this is in the optimal OLS setting. This is not by chance. This is due to the so-called bias-variance trade-off, and the exact mechanics are shown in another video. Here I'm just demonstrating how you can beat OLS, and you should beat OLS in theory in its most favorable setting. Thanks for watching.